right. Can't seem to silence my iPad completely. So not sure why. I have to plug in some headphones into the iPad. So one of you may know the solution to this problem. I plug in a fake headphone just so that it doesn't produce any noise, and then I've turned the volume all the way down. Anyway, I have a way to make it work, so it's fine. So how are you guys doing? Still holding up? Okay.
Very tired.
Tired? Yeah. Oh my. All right. But optimization is exciting, right? So that keeps you awake, correct?
Yes. It's my wake up for the day.
All right. Okay, so let's briefly review what. Oh, I should mention that our midterm is coming up in a little bit less than 2 weeks, right? The Monday, 2 weeks from yesterday, essentially. And it'll be done through CBTF and Gradescope. So basically, I think there'll be a way in which, some way in which you'll access the PDF file of the exam. Have all of you actually taken some exam through CBTF already, or probably not all of you have, right?
No, I haven't.
So the procedure
I haven't, yeah.
Yeah, so some of you probably did, but if you don't, we'll talk about it again later, but as we get closer to the date of the exam. But basically, CBTF proctors the exam. You get to download the PDF file of the exam either through Gradescope or from others' secure website, and then you take the exam and then upload the solutions up to the to Gradescope. Now, I need so if this was an in-class exam, physical exam, not an online exam, I would have. I would allow you to use a sheet of notes, and that would be, one. In fact, that's what I have written on the website. But that may not make sense for an online exam. So it's really up to you. I mean, it's still probably convenient for you to have a sheet of notes, but I probably make the exam so that it's that if you want to be open notes in the sense that you can have at least my handwritten post-class notes, you can have all of it available to you, or you can either print it out or have it in some other form, and that should be fine. But I would still encourage you to make that one sheet of summary notes for your own convenience when you take the exam.
So for the CBTF, what exactly is this for? So we are not uploading the solution there?
No, CBTF is just a way to proctor your. So there will be people who are proctoring you on Zoom, just like,
Okay.
You would have to use your phone and show your workspace, and they'll time the exam and stuff for you. But at the end,
so we cannot have it in laptop.
You can have your exam displayed on your laptop, and I think you use your phone camera for the proctoring itself. And I'll make it open notes in the sense that you can have you can look at your notes. But I think it'll be easier on both of us if I'm not completely decided about that. it'll be easier probably if I insist that you guys make a sheet of notes that you consult, like a handwritten sheet of notes that you consult during the exam, instead of keeping, if you're going to use your computer to look up my class notes, then it'll probably take you a lot more time, and also you know, it'll be harder for the CBTF people to proctor you. So I think it might make sense for you to have a set of you know, handwritten sheet of notes that you can keep. But if you want, you know, I can't stop you from. It'll be hard to enforce and stop you from making, you know, printing out all my notes and having it on the side for you to consult. So that I can allow that if you want, if that's what you guys prefer. That'll make it easier for the proctors, because if you're going to rely on looking at your computer screen to get the notes, then it'll be hard for the proctors to also keep you from going and looking at other resources, or, you know, going to websites where you can communicate with other people to get answers to the questions. So that makes it much harder for the CBTF people. So so maybe we can make it open notes or open book, but not open resources from the internet. So you can either, you know, have a hard copy of my handwritten notes next to you, or you can make your own version of your handwritten notes or summary or something like that that you can keep on the side. So yeah, so it's something that I think we'll have to see what works best. So I'll also consult the CPTF people, and I'll get back to you probably next Thursday. So next Thursday, which will be the day before the quiz, the class before the quiz, we'll do a review session about the exam and so on. And in that review session, we can also finalize how we're going to deal with the notes. Okay. Right. So more will be coming on that. Okay. So let's quickly review what we were talking about last time, because today's lecture is going to take a little bit longer. It's a little more involved than some of the previous lectures. So I want to go through the previous material a little more quickly. So we talked about constraint optimization last time. And in particular, we were talking about the case where we want to minimize some function over a set S that is non-empty, closed, and convex. Okay. In that case, we can derive some necessary optimality conditions, essentially necessary and sufficient, and the optimality condition is that basically the gradient dot product with the gradient and x minus x star should be greater than or equal to 0. Which if and this would basically only be relevant for the case where the minimum occurs, the local minimum occurs on the boundary, because if the local minimum is in the interior, then the gradient, the old condition still hold, that the gradient should be 0, okay, at a local minimum. So for interior local minima, the gradient is still going to be 0. For boundary local minima, the gradient has to satisfy this condition, okay? And if f is convex, then this condition is also sufficient for x star to be a global minimum. Okay, so, and then we went over the proof of that. And then here, again, let's re-emphasize that. If x, because we're going to use it in today's lecture, if x star is an interior point of S, then x star is a local minimum, implies that the gradient is 0. Okay, and of course, if it's convex, then that's also a sufficient condition for it to be a global minimum. So basically, everything that we did before for unconstrained optimization applies if x star is an interior point of S. Okay, and basically all those proofs go through unchanged. Okay, and then we talked about the projection theorem. And basically, projection of a point onto a set S, onto a closed convex set S, is given by the point that's closest in L2 distance, or squared norm distance between Z and any point in that set S. Okay, and we had a necessary and sufficient condition that we derived for that, and then we also showed that the projection is non-expansive, that the distance after projection is going to be smaller than the distance before projection. Okay, and then we used these results to discuss the convergence of what's called the gradient projection method, where basically you do gradient descent, but each step of the gradient descent, you project onto the set S, the constraint set S, to make sure that you're always in the constraint set. And we showed that this method will actually converge to the minimum if F is convex. And in fact, we used the strong convexity condition to establish a basically identical result for the rate of convergence as in the unconstrained GD, except that this projection operation that you need to do might be computationally expensive in many situations. And for some special cases, and you'll see another special case in your homework, these projection operations are easy, but in general, that computation might be close to, in terms of complexity, to the original optimization problem. I said there are other methods that one can use to solve constraint optimization problem when the constraints have a certain form, and that's what we're going to start studying today. Okay, so this is optimization with equality constraints. That's today's topic. All right, so what we said before was we were trying to minimize a function with x being constrained to some set S. But instead, now we're going to actually specify exactly how that set is constructed, and we say we're going to be constructing that constraint set through these constraints. Okay, h1x equal to 0, h2x equal to 0, maybe up to m constraints, hnx equal to 0. Okay, and you can combine all of these guys into a single constraint, a vector constraint, vector function, a vector valued function h of x equal to 0. So basically, where the vector valued h has as a component h1x, h2x, and hnx. Okay. Any questions about the problem setup? Okay. So the function is Rn to R, real valued. Each of the hi's are real valued, and if you combine them into a single h, that will be sitting in Rn. Okay. Now, h is continuous. Then the constraint set, let's denote that constraint set by a script h, which is all the x's for which the constraints hold, hx equal to 0. This set is a closed set. And in fact, you're going to show this in your, if you don't already know this, that's the first homework problem in homework 3, which if you have started, you should have shown this. It's very easy to show that this is a closed set. Okay. But not necessarily convex. So we can't apply the machinery that we talked about in the last class. It's closed, but not necessarily convex. So hx equal to 0 gives you a closed set, but it's not necessarily convex. And let's do some examples. If hx is of the form A transpose x minus b, so it's a linear constraint of this form, then under this linear constraint, the constraint set script h basically is when little h of x is equal to 0, which is A transpose x equal to b. What kind of set is this? Anyone?
Plane, hyperplane.
It's a hyperplane. Very good. So it's a hyperplane, and a hyperplane is convex, right? Okay, and this is very easy to show that it's convex. Just take a convex combination of of x's and show that that's still going to be in the set. That's trivial, right? So this is a convex set. But what about the set h of when h of x is the norm of x minus 1? This is like a sphere, and in 2 dimensions, it's a circle. Okay, so if I have x1, x2, okay, this is a circle, but it's just the circle, not the interior, just the boundary of this this sphere. Okay, it doesn't include the interior. So it's basically the surface in general, in n dimensions, it's a surface of the unit sphere. So the constraint set is the surface of the unit sphere. And this is not convex. Is it obvious that it's not convex? So very easy to construct a counterexample to show that it's not convex. Say in this case, just take this point and this point, take a convex combination of half for both of these points, and you sit in here, which is not on the circle. Okay, and you can do this in any number of dimensions. Take the first coordinate and make it look at +1 and -1 as the 2 options for the first coordinate, and the linear combination of that with half will take you to the origin, and that's not on the surface of the unit sphere. So this is not a convex set. Okay, but it's closed. Right? Okay, so now let's assume that the f's are not just continuous, but f's and the hi's are continuously differentiable. And what we're going to show, and that'll be most of this lecture, is that if x star is a local minimum for this optimization problem, the constrained optimization problem, this one, okay, then there exists the lambdas, which are called Lagrange multipliers. Okay, or H or belonging to R, such that the gradient at x star of f plus a linear combination of the gradients of the h's is equal to 0. I'll call this equation star. Okay. So again, I said under appropriate conditions, and we'll see what those conditions are. So under some conditions, we'll show that if x star is a local minimum, then there exist these lambdas such that the gradient of f at x star can be expressed plus a linear combination of the gradient of the hi's is equal to 0. Okay. All right. Okay, so before we actually get to proving this, let's see what this means, what this equation means, equation star. So there are 2 ways to interpret this. One is that this says that the gradient is the negative of the linear combination of these gradients at x star. Okay. By the way, the lambda i's could be positive or negative, so coefficients multiplying the gradients of hi's could be either positive or negative. So it's some linear combination essentially of the gradients of hi. So this means that the gradient of f at x star belongs to the space, which is the span of the gradients at hi. Gradients of hi at x star, sorry. What's the span? The span is the space of all vectors, right? N-dimensional vectors in this case, that are linear combinations of the things in the span. So the linear combination of the gradients of the hi. So since I can express my gradient of f at x star as this linear combination, it belongs to this span, the space. Okay, what's the dimension of this space? Well, this space actually has dimension given by the rank of the matrix formed by putting all these guys into, if I put all these vectors into a matrix, the rank of that matrix tells me the dimension of that subspace. And so this space, a G of X star, is an m-dimensional subspace if and only if the HIs are what? The gradient HIs, what condition should they satisfy?
Linearly independent?
Yeah, very good. So they have to be linearly independent. Or in short, we'll write that as Li. Okay. So that's one way to interpret it. So, so that the gradient of f at x star belongs to the span of the gradients of the HIs. Okay, another way to think about it is that the gradient of f at x star is orthogonal to a subspace that's orthogonal to G of x star. So we'll call that V of x star. So it's orthogonal to this subspace. The subspace is all the vectors Z belonging to Rn, such that the gradient of, if I take the inner product of the gradient of the HIs with Z, that has to equal 0 for I equal to 1 to M. So this subspace basically is orthogonal to the span essentially, and since gradient of f is sitting in the span, the gradient of f is orthogonal to this subspace, right? And it's easy to see why that's true, because if you look at the gradient of HI of x star transpose gradient of f of x star, since that is just a linear combination of the HIs, it's going to equal 0. Okay, so there are two ways to interpret it. That either the gradient of f of x star is the span of the gradient of HIs, or it's basically sits to it's orthogonal to this V of x star subspace. But there's another way to interpret V of x star. V of x star is a space of first order feasible variations at x star. So, so remember that you have some constraints, right? So just like, for example, the circular constraint that we had in 2 dimensions. And so what are the feasible directions? So you have to remain on the circle. So at any point here, I can go this way or that way locally, but that's all. I can't go this way, I can't go that way, right? So those are the first order feasible variations. But why is V of x star the one that satisfies these conditions? Why is it the space of first order variations at x star? So for example, let's say x star is this point here. So why is the space of all first order feasible variations at x star captured by V of x star? And that's actually fairly easy to see. This is similar to things we have done before. So let's actually perturb x star a little bit. So we know that h of x star must be 0, but let's look at h of x star plus some alpha times z, where z is an arbitrary direction. So if I'm still going to be feasible after perturbation, right, by z, then I must have for that z that h of x star plus alpha z equal to 0 for alpha sufficiently small. Otherwise, it's not a feasible first order variation. Okay, but then let's see. So if this is the case, I still remain in the constraint set after I perturb by alpha times z, but my original value h at x star is also 0. So but I can write this. Let's say, let's look at HI in particular. There could be more than one H. This is plus, I can use Taylor's expansion to write this as HI of x star transpose Z plus little o of alpha. Okay, This is just from Taylor's expansion, but this guy is 0 because that I started off an X star that's satisfied the constraint and perturbed it a little bit and still satisfied the constraint, right? Now, if I divide by alpha and take the limit as alpha goes to 0, what we get is that the right-hand side has to be 0 after division by alpha, so gradient of hi of X star equals 0. So what this means is that for any first order feasible direction Z, right, I must have gradient of hi X star transpose Z equals 0. Okay? So you can interpret V of X star as a space of subspace of first order feasible variations at X star. Is that clear? All right. And we'll see how this V of X star plays a role in the Lagrange multiplier theorem a little bit later.
Excuse me.
Yeah.
Did we like skip a line of notes next to the Y? Is there supposed to be something in that blank?
Which Y?
Right in the middle of the screen.
The middle of the screen?
The question why.
Yeah. So yeah, I'm answering that question.
Oh, so that whole thing below it is must satisfy
the answer to that question. Yeah. Why is V of X star considered to be the space of first order feasible variations? This is why.
Okay, thank you.
Right. All right. First, let's look at an example. Oh, actually, before we do this example, I want to show you a figure from the book. Okay, just illustrate the notion of Lagrange multipliers. So this is a minimization problem. I'm trying to minimize this linear combination x1 plus x2 such that I lie on the two-dimensional sphere. So the constraint set is this circle essentially, just not the interior of the circle, but just the circle. And I want to minimize x1 plus x2. So these lines, the lines that are drawn here, correspond to x1 plus x2 equal to some constant. Okay, so this line, this line, and this line, and this line, they're all, I'm drawing all the lines that correspond to the function. Various values that the function can take, x1 plus x2 equal to something, and I'll get this line. Now, I need to be in, I need to satisfy the constraint. So I need to only be looking at x values in this two-dimensional space that are on the circle. Okay, for example, for this this choice here, this line here, I can look at this and this, okay, as my feasible values. And then so basically I can't move off of this. If I have a line that is here, for example, like here, then it's outside the circle, so there are no feasible x on that line. And similarly, if I have a line that's here, there's no feasible x on that line. So all the feasible x's are going to be correspond to lines that are between this line and the line of this boundary. And among all those lines, I want to know which one gives me the smallest value of the function f, which is this. And of course, it's obvious for this picture that basically it's the one that will be this will correspond to the smallest value of f, right? This extreme line here. So that's x1 plus x2 equal to -2. Okay, so the minimum value that this function can take is -2, and that occurs at the x star, the minimizer. The minimizer is at -1, -1. Okay, which satisfies the sphere constraint and minimizes x1 plus x2. So you can see by picture in this case, of course, in more complicated examples, you couldn't solve the optimization problem by picture, but in this case, you can solve it by picture, and you conclude that this is the optimum value. Now let's look at the gradient of the function at this value, right? So what's the gradient? Well, the gradient I can compute, actually, the gradient in this case is easy to compute. It's just 1, 1. Okay. So the gradient vector basically goes in this direction from here. This is the 1, 1 point, so it goes in this direction. So in fact, at this point, basically the gradient is going this direction. And if I look at the gradient of h, right, that's 2x1, 2x2, which you can compute easily from there. And you see that the gradient of h at -1, -1 is -2, -2 going in this direction. This is the point -2, -2, so it's going in this direction. So what this is saying is that the gradient of f is collinear with the gradient of the constraint. And that's exactly what the Lagrange multiplier result is saying, right? And in fact, what is that multiplier in this case?
-2.
No, negative, actually plus half, right? So the Lagrange multiplier is actually plus half, because basically you want gradient of f at x star is equal to minus lambda times gradient of h at x star. So this one is -2, -2. And if you multiply it by -0.5, you get 1, 1 on the side, right? Okay. All right. So, but the point of this picture was to show that the gradient is collinear with the gradient of f is collinear with or it's basically sits in the span of the gradient of h of x star. There's only one of them. That's why it's just going to be on this line. Right, is that clear? This is just an illustration that that result might make sense. But actually, now let's do an example where we may not have this happen. And this is an example where there are no Lagrange multipliers. And we'll then give a reason for why that may not happen. So let's look at this optimization problem. We want to minimize x1 plus x2 again, but now we have two constraints. One is this. We want to be on this circle, okay? And the other one is the slightly larger circle. So you have to be on both of these circles. So if you want to be on both of these circles, there's only one point x star that's on the intersection of both of these circles. So this is the only feasible point, okay? Okay, we'll come to that in a minute, but this is the only feasible point. So if there's only one feasible point for this minimization problem, what's the solution to the minimization problem? If I have to minimize f of x over a set which contains only one point, what's that minimum?
It's that point.
It's just that point. What's the maximum? It's also that point, right? So if you have only one point, you've solved the problem already. From the constraint side, okay? So if the constraints lead to something unique, and we'll actually revisit this a couple of times later, if the constraints lead to something unique, then you've already solved the problem. There's nothing to be done. Okay, there's no variation in f. Okay, so let's compute the gradients in this case. Easy to do. It's still, this one's still sorry, let's change color. This one's still 1, 1. Okay. Sometimes we write this as just the pair 1, 1. So either you write it as a vector or you write it as a tuple. And then if you look at the gradient of h1, that's going to be 2x1 minus 1 and 2x2. Okay, and h2 is 2x1 minus 2 and 2x2. Okay. So as we said, that there's only one feasible point, which is 0, 0. So x star is 0, 0. That's the solution of the problem. But let's look at what the relationship is between the gradient of f at x star and the gradient of the h's. The gradient of f at x star we already computed. This is just 1, 1. the gradient of h1 at x star is -2, 0, and the gradient of h2 is -4, 0. Okay. So now let's try and take linear combinations of the h1 and h2 and see if we can produce this. Well, there's no way to do it, right? Because the second component of both of these h gradients are 0. So there's no way, no linear combination of these that can produce a 1. This means that there is no choice of lambda1 and lambda2 that makes gradient of f at x star plus lambda1 times the gradient of h1 at x star plus lambda2 times the gradient of h2 at x star equals 0. But you can see why this is happening. Why is this happening? Because if you look at this, the span of these two vectors, it's one-dimensional space, right? That's because the gradient of h1 and the gradient of h2 at x star are linearly dependent. They're not independent. Okay? And that's why we have this problem. Now, this is not to say that you have to have linear independence in order to find Lagrange multipliers. And we'll, probably next Tuesday's lecture, we'll give examples of, you know, how you can find Lagrange multipliers, even even though the gradient. So there are some examples where that can still happen. So, but in this example, the reason why we are not able to find Lagrange multipliers is because of this linear dependence. They're not linearly independent. Okay. So is this example clear to everyone? Any questions? So what we're now going to say is that let's make these guys linearly independent, right? And we'll give that a special name. So we'll say that a feasible x belonging to the constraint set, that means the h of x is equal to 0, is called regular if the gradient of the hi's at that x are linearly independent. Now, one remark, immediate remark, is that for these gradients to be linearly independent, we need m to be less than or equal to n. Why? Say I have, say n is equal to 2, and I have 3 two-dimensional vectors. Can they ever be linearly independent?
No.
No, right? So m can at most be equal to n for them to be linearly independent. So in order to have a regular x, okay, the m has to be, the number of constraints has to be less than or equal to n. Okay, so now we'll state the Lagrange multiplier theorem, and then we'll spend the rest of the lecture proving it. Okay. So let's look at the first order necessary condition. So suppose x star is a local minimum of f subject to h of x equal to 0, and assume that these are linearly independent at x star. So x star is regular. Okay. Then there is a unique set of lambdas, a unique vector lambda, lambda 1 through lambda m, such that this condition holds, the condition we've been talking about. Okay, so before we get to the proof, let's actually have another side remark here. What if little m were equal to n, and these are linearly independent? Then this equation holds trivially, I claim, because in that case, if I look at these edges, the gradient of h's, it's a linear independent, and there are n of them, and they're n-dimensional vectors, and I have n linearly independent n-dimensional vectors. They form a basis for Rn, right? Form basis for Rn. Okay, since they form a basis for Rn, then I can express any n-dimensional vectors in terms of them. And so in particular, I can express gradient of f at x star in terms of these guys. Right. So it's you get it trivially. So you really only need to consider the case where m is strictly less than n in proving the Lagrange multiplier result, because the case m equal to n is automatically covered. There's nothing to prove. It's not surprising. Okay. All right. I think let's take a short break, and then before we get to the proof. But I should mention that there are two approaches to proving the Lagrange multiplier theorem. They're both, equally complicated. But I'm going to only do one approach, what's called the penalty approach here. And if you want to read the other approach, and that's called the elimination approach, it's in section 4.1.2 of your textbook. The reason why I chose to do the penalty approach is because the notion of adding a penalty to helping solve constraint minimization problems is actually useful. It'll turn out to be useful later when we talk about computational approaches to solving constraint optimization problems. So I wanted to introduce that idea a little bit earlier in the course. That's why I chose this proof. But if you want to look at the other proof actually requires the use of what's called the implicit function theorem, which is again described in the appendix of your book. So I would encourage you to look at that, because there may be some other insights you can glean by looking at that proof. But I don't have the time to do both proofs in this course, and I'll probably bore you by doing that anyway. So we'll look at only the penalty approach. Okay. So any last minute questions before our short break? Right. If not, we'll convene back at 11:44. Okay, so let's get started with the proof. Any last minute burning questions before? Okay, before we start. Okay, so what's a penalty approach? So we're going to relate the constraint optimization problem to something we know about, which is unconstrained optimization, right? Which we have studied in great detail so far. So let's take the function f and add to it a couple of things. That's why this is called a penalty approach, because I'm going to add to it something related to the constraint. So I'm going to add h of x squared. Okay, and you can think of this term as a penalty for violating the constraint. Because the more you violate the constraint, the larger the norm of h of x will be. Okay. And then I'm going to add to it another piece. And this would try and take my function g and force it to be close to its minimum, to be close to x star. Okay. So I do this for k equal to 1, 2, and so on. So this, remember, this guy here is a strictly convex function around x star. So let's try to attract x to x star. Okay, so this is a sequence of functions. So I'll index it by the superscript k. All right, and and as I said, there's this penalty term here, and this is a term that you'll see the use of that term as we go through the proof. So any questions about the form of this function, gk?
So what is the subscript of k in G?
Superscript k, just a way to index the function. I don't want to use subscript because that will confuse with the subscripts that we're going to be using for that, you know, in iterations of that we use in iterations of gradient descent and so on. So I just put a superscript on the function to index the sequence of optimization problems. That's all. Okay.
So we will have, yeah. So we will have multiple
multiple functions.
Right?
Yeah, multiple functions G. So that's, yeah, basically we have a sequence of functions k equal to 1, k equal to 2, and we'll see what happens, how we use these functions in just a minute. Okay.
Yeah.
Now,
okay.
X star is a local minimum of f under the constraint set script h. We know that the definition of local minimum is that there exists as epsilon, might be small. You can choose it to be as small as you like, but it has to be positive, such that if I look at any x in a ball around x star with that size epsilon, I should be able to make my f of x star be smaller than every value in that ball. So for all x belonging to h and everything belonging in the ball. So I'll just write that as h intersect s, and I'll use s to denote the ball in this case of size epsilon. Okay. So that's a definition of a local minimum, right? Local minimum says that if I look at a ball around x star, then the value at x star should be smaller than all the other values in that ball. Sorry, this is less than or equal to, I guess. It's not strict necessarily. And then but we have to also meet the constraints. So we have to be in this set H. Okay. All right. Okay, so that's a condition to keep in mind. We'll use this a little bit later, but keep this condition in mind. Now let's look at the function gk, and we actually want to solve gk as an unconstrained problem, but it'll turn out that it'll be easier to first look at it, look at the solution to this gk function, the minimization of this gk function under a constraint on x belonging to this ball, okay, this epsilon ball. And then we'll see why actually solving that constrained optimization problem is equivalent to solving an unconstrained problem in just a minute, okay? So first, let's look at this problem. Let's call this PK. PK is a problem where we're trying to minimize GK subject to X belonging to S, okay? Now, we know that there's a solution to this problem because there is a minimizer. Why is that? Because S is compact. Right? S is all the values of X that are sitting in this epsilon ball around X star. X star is some, some value in Rn that's not infinity, right? It's a well-defined value in Rn. So I put a ball around it. Everything in that ball is going to be bounded, and the set is closed. Oh, it's not going to be closed if I don't include epsilon. Sorry. Let's include epsilon. I don't know why I'm not writing my inequalities properly today. Yeah, so this has to include epsilon, and that's what they'll make it a closed set. And you again in your in homework 3, I'm just revisiting the idea of closed to an open set, so you know that these kinds of sets are going to be closed, defined by inequalities like this. Okay. If it was strict without the equality here, it would be an open set, but I need the equality to make it a closed set. So if I have a closed and bounded set, which is compact, which means that there is a solution, optimal solution to PK, right? Exists by Weierstrass's theorem. Okay, so I know that there's a solution, and I'm going to call that xk. So xk, remember, is the solution to this constraint optimization problem. Now I'm going to establish that xk converges to x star as k goes to infinity first. X star, remember, is the solution to my original optimization problem, right? A local minimum for my original optimization problem. Okay, first let's look at the by definition, gk of xk at the optimum value is f of xk plus, k over 2 h of xk squared and so on. I'm just plugging in xk in terms of x, in place of x on the right hand, in this equation here. Okay. Now this thing, remember that this gk of xk is the optimum value, is the smallest value of gk that gk can take. So it's going to be less than or equal to gk of x star, which is equal to f of x star. And let's call that equation 1 on the set S. Okay. Now, since oh, I should, and this is true on the set S, but x star is obviously an element of the set S, right? Because x star is inside this ball, right? That's why I can write this. Now, f of xk is bounded over the set S. It's a nice, it's well-behaved function, right, over the set S, over this compact set S. Okay, so this guy, as k goes to infinity, this guy is going to remain bounded, right? And this guy is, of course, also going to remain bounded. Okay, left-hand side is also bounded. But then what happens is that now, but this k multiplying this guy is going off to infinity. So the only way this whole thing on the right-hand side can remain bounded is if h of xk goes to 0 as k goes to infinity. Okay, if h of xk didn't go to 0, or the norm of h of xk didn't go to 0 as k goes to infinity, the left-hand side will blow up to infinity, which cannot happen. So every limit point of xk must satisfy h of x bar equal to 0. And that means it's a feasible point from my original constraint set, right? From my original optimization problem. It belongs to the constraint set H. Okay, so that's one thing I have. So I have H, any limit point of xk, right? I've not proved yet that xk converges, but if any limit point of that must satisfy the constraint h of x equals 0. All right. Now the next thing we'll see is that the condition 1 up here, this condition implies that, so I've got this plus some positive number plus this less than or equal to f of x star. But if I remove any of these things, it'll still be less than or equal to the right-hand side. So I can remove this term, either of these terms, but I'll remove this term, and the combination of these two will still be less than f of x star, right? Because I'm taking away something that's positive. So f of xk plus just the last term is less than or equal to f of x star. Okay, so I'm going to use these two facts now to show that xk converges. I'm going to use this fact and this fact to show that xk converges. Okay, so how do I do that? Okay, so I've repeated that statement here. Now let's take the limit of xk. So it's xk goes, say, to this limit point x bar. So every limit point x bar must satisfy the same inequality with xk replaced by x bar in the limit. That's clear, right? Now we know that x bar belongs to h. Also, x bar belongs to s. Why is that? Because basically all the xk's have to belong to s by construction, right? We are only looking at, in these optimization problems, we're restricting my x's to s. So all these xk's must belong to s for every k. Okay, so then this means that x bar belongs to the intersection of h and s because it belongs to both of these sets. Now let's go back and see what the definition of our f of x star. This says that any point that belongs to the intersection of h and s must have f of x star being less than or equal to f of x. Our x bar now will go on the right-hand side, and so we can conclude that now f of x bar is less than or equal to f of x star is less than or equal to f of x bar, because x bar is a point in the intersection of h and s. So by the fact that x star is a local min, I get that. But then I look at these two equations. So if I look at the equation that this inequality that I started off with, So this is f of x bar, sorry, not x star, plus alpha over 2 x bar minus x star squared. That I get should be less than f of x bar again from the previous inequality. So the only way this can happen is I'm going to have to get rid of this term and this that says that this something, a square of something is less than or equal to 0. The only value that it can take then is just 0, right? So that this means that x bar minus x star is equal to 0. That means every limit point is equal to x star. And what does that mean? It means that the limit of xk exists because all of the limit points are equal to x star. Okay, is that clear? So what we have shown now, let's go back and see what we have shown. We've shown that if we look at solutions to this constraint optimization problem, xk, those solutions all go to x star. Okay, why is that important? Okay, so now let's look at the S, the set S again. The set S is the ball around x star, right? So you have x star here, and it's an n-dimensional ball of radius epsilon sitting around x star. That's my set S. Okay, I mean everything's included in this. That's inside the interior. So x star is actually has to be an interior point because there's a non-zero epsilon ball sitting around it. So x star is an interior point of S by construction. Now xk is approaching x star as k goes to infinity, right? So I can make it as close to x star as I want. So as xk starts to approach x star, I can get inside this ball eventually, and so xk will also become an interior point for large enough k. For k sufficiently large. And you can make this more precise if you want, but those kinds of details are only important, you know, for when you're taking a preliminary course on real analysis. But you can make the you can see exactly what sufficiently large is if you like, but we're not going to go over those kinds of details here. Makes the proof unnecessarily long. Okay, so eventually, basically, my xk is sitting inside this ball, so it becomes an interior point of S. So, but if xk is an interior point and a minimizer of gk, what do we know from lecture 10? Let's go back here.
Gradient 0?
Gradient has to be 0, exactly. Very good. So the gradient of gk at xk must be 0 for k sufficiently large. Okay. Now let's go back to see what gk was, so we can compute its gradient. Gk is this. So the gradient of this function can be written as gradient of f plus, okay, now I have a gradient of h squared. So how do you compute this gradient? Well, this is going to be, let's apply the chain rule. So this is going to be the gradient of h, okay, multiplied by hi of x. So hi of x times the gradient of hi of x, and then I sum them. But then there's a factor of 2 because basically I have, this is like hi of x transpose hi of x. So I'll get a factor of 2 from by taking the gradient from the squaring operation essentially. So I'll just get k. By the way, this is not clear to you. Go back and from first principles show that this is the answer. Okay, for when I take the gradient of norm of hi squared, I'll just get hi of x times the gradient of hi of x times 2. So I got rid of the 2 on k. And the gradient of this guy, this is easier to compute. This will just be 2 times x minus x star. This will cancel this 2, and then I'll just get alpha x minus x star. Okay. And I know that if I plug in xk in this equation, I should get the left-hand side would be 0. Okay, well, I'll exploit that in just a minute. For a k sufficiently large, of course. But before we get to that, let's define a matrix. Okay, and we mentioned this matrix before, but take all the gradients of all the h's and put it into a matrix. So it will be an n by n matrix, n by m matrix, which is all the gradients and put together. What's the rank of this matrix?
M.
Yeah, so this has rank m because the columns are linearly independent. And m is strictly less than n in this proof, okay? Because if m is equal to n, we showed that the result is trivial, right? This has rank m. So this is at x star, it has rank m, but xk is approaching x star. And so by the continuity of the gradients, this is also going to have rank m for k sufficiently large. Okay, because I can make my gradient at xk. So xk is approaching x star, so the gradient of h at xk will approach the gradient I can make it as close as I want to the gradient at x star by making k sufficiently large, right? So this holds by the continuity of the gradients. So these HIs at xk will also be linearly independent. Okay, so now let's introduce do a little sidebar here. We'll introduce a notion of a pseudo inverse of a matrix that's not square. So let's look at a full rank matrix. So it's an n by m matrix. N is bigger than or equal to m. In this case, actually, we are looking at the case where it's strictly bigger than, but it's the same thing holds. And suppose it has rank m. Then A transpose A is an m by m matrix that has to be invertible. You know that from linear algebra, right? And so we can take its inverse, and then if we post multiply that inverse by A transpose, you get a new matrix, okay? And that matrix is an m by n matrix, right? Because A transpose A is m by m, and this is an m by A transpose is an m by n matrix. So this whole thing is an m by n matrix. And this is called a form of a pseudo inverse of A. And it's actually like a left pseudo inverse of A, because if I multiply this guy by A, I get an identity matrix, right? Because this guy and this guy will just nullify each other. I get the identity matrix. So left multiplication by this matrix left multiplication of A by this matrix will give me the identity matrix. That's why this is called a form of a pseudo inverse of this non-square matrix. Okay. Okay, this is also sometimes called the Moore-Penrose pseudo inverse. So if you want to read more details about that, I think that the appendix in your book has discusses it. But any course and any textbook on linear algebra will talk about that. So what's the use of a pseudo inverse? One use of a pseudo inverse is to solve a bunch of linear equations. So if I look at a set of linear equations, this is a set of linear equations, m linear equations, and n unknowns, where m is less than or equal to n. Then I can solve and get a unique solution for z, which is I can solve for z, and this is a solution for z, right? Through the pseudo inverse. Because if I pre-multiply by the pseudo inverse, okay, I just get z on the left hand side. So that's how I get this. Okay. All right, so I'm going to exploit the fact that I can get a solution for az equal to b through this Moore-Penrose pseudo inverse. Okay, and the proof. So let's see how we do that. So let's start by rewriting this equation for the gradient, which we just saw on the previous page. This guy that we just computed here, we'll read and just rewriting that equation here. Okay, and then I plug in xk. If I plug in xk, I get 0. So I have xk on the right hand side everywhere here. And then I just simplify. I just take this term and take these two terms on to the other side. So if I did that, since this is 0, I get k times this. So that is minus this minus that. So that's that. Okay, but now I have a form. So this is like this matrix, right? Oh, by the way, I should have mentioned, maybe I didn't do that. If I look at this linear combination here, this linear combination can be written as this matrix times h. Okay, so if I multiply this matrix times h, which is h1 through hm, okay, I'll basically get this linear combination. So that's I've taken this matrix. Grad h is this matrix, this n by n matrix times this vector h. That's what I've substituted here. Okay, so that gives me that linear combination, this linear combination. Okay, I should have mentioned that step. Okay, so now I have this matrix. This is a matrix, the gradient of this vector function h, which I denoted by this matrix, times the vector h of xk is equal to this. So this is of the form az equal to b, okay, where a is this matrix and z is this vector times k, if you want to absorb k into that vector. So k times that vector must be the negative, right, of the pseudo inverse of this h grad h matrix times this vector. This is like my b vector. So if I now look at the limit of this guy as k goes to infinity, this is minus and I'll denote that this is a vector now. So this is a matrix, pseudo-inverse matrix times this vector. and I'll call that lambda. Okay, so this is a vector, m-dimensional vector. So this pseudo inverse, as I said, this is an m transpose. Let me make sure it's all correct. N by m, A transpose. So this whole thing is a m by n. So not h. So this is lambda. Sorry. Yeah, this is lambda. Same dimension as h. Right. So this is, in this case, this matrix is. So this is. Let's make sure we have a span here. This is m by 1. This is n by m, and this is n by 1. Okay. So what I end up with at the end is going to be an m-dimensional vector lambda. So this I'll call this limit to be my lambda. Okay, and let's see what role lambda plays by revisiting this equation. So let's revisit this equation now. So we know that this guy converges to lambda as k goes to infinity. So let's take the limit as k goes to infinity here in this whole equation now. So what happens then is that this guy is going to x star, right? This guy is going to x star. Of course, yeah, it's set the right-hand side equal to 0 because I used the gradient condition. I just proved that this is equal to lambda, and then we have this guy going to 0. So if you take the limits, I get that the first term just goes to gradient of f at x star plus gradient of h, the gradient matrix, basic at x star times lambda equal to 0. But this gradient matrix times lambda, this is the sum from I equal to 1 to m of lambda I gradient of h. Okay, so we conclude that this is true. All right. Any questions?
Professor, I have questions for go back 2 slides probably.
Yeah.
Yeah. So you said sorry, I'll probably go forward 1 slide. There's a rank.
Okay.
Yeah. So you said the gradient of h has rank m, and when k is sufficiently large, then we also have the gradient h at xk is rank m. But it seems like it's possible to like infinitesimally perturb a, say, rank m minus 1 vector and get a rank m vector.
No, that's impossible by continuity of the gradient of h. That's why we're exploring the continuity. So by continuity, you can't change the gradient of hi's by an arbitrarily large amount by just perturbing xk by x star by a little bit, right? So you can't make a huge change, and so you should always be able to find some delta that that's small enough such that your gradient of the HIs at xk is within delta or delta ball of the gradient of the HIs at x star for all I.
Oh, I think I'm saying like a inverse. So imagine we have a dimension m vector and it's rank m minus 1. And
Right.
it is possible to perturb that vector infinitesimally to get a higher rank vector.
No, I don't think you can. Not by infinitesimal changes.
Okay.
No, it's not possible. Unless one of the elements was infinitesimally small to start with, but that's not, but it's still some, non-zero value, right? So you can still be, so suppose you're very but you're talking about ill conditioning, I think, where you might have some elements of the vector be really small. But no matter how small that is, for example, right? So that so if you perturb by more than that small number, then you might lose the full rank property. But what I'm saying is that no, we're going to actually choose my k large enough that you're still within that perturbation.
Okay, I see.
Right. So I can always make it full rank for sufficiently large k.
Yeah, thank you.
Right. Any other questions? Okay. So I mean, the proof is somewhat complicated. Okay, and I don't expect you to remember the proof. I don't think I could too. After a few days, a few months, but I thought you need to see the details of this proof at least once in your life, and then this is the course to do it in. Okay, but mostly what we'll be using the result, which is this. Okay. Okay, so next lecture, what we're going to do is look at second order necessary conditions. This is only first order. Let's look at second order necessary conditions, assuming twice differentiability, and then sufficient condition that we can derive. And then we'll start doing some examples. So towards the end of next lecture, and then all of next Tuesday, we'll do a bunch of examples of how to apply the Lagrange multiplier result for equality constraints. And after we are done with that, that'll be basically after your exam, we'll start talking about inequality constraints when we have things like g of x less than or equal to 0 rather than h of x equal to 0. Okay. All right. So I'll talk to you guys on Thursday.
Yes.
All right.